Hello and welcome to the LMI webinar series. My name's Aaron and I have with me today Chris Hooper is our territory manager, and he'll be going over the surface filtering tools, just some of the basic tools to kind of get you started. We're going to get your feet wet on this and give you somewhere to start with. And also we have Bobby Breyer, our field application engineer. He'll be going over some of the profile surface tools towards the end of today's webinar. Just a few things before I hand it off. Just note that if you want to ask any questions during today, we are doing this live, but you'll have to use the chat function. You'll see it on the right-hand side of your screen. Just type it right in there. We will do our best to answer all the questions if we have enough time. There'll be a little Q&A at the end. The second part is this is being recorded, so if you have to step away at all, don't worry. In about 2 hours, you'll see it in your email, and there will be an automatic recording. Also, we'll put this up on our LMI YouTube channel. So without further ado, Chris, I would like to open it up. Well, Chris and Bobby, any opening remarks before we get started?
No, just want to say quickly that the surface tools we're going to review today are some of the more basic or perhaps some of the more commonly used ones. And then we will follow this up with covering some of the more advanced surface tools with another session in May.
Yeah, I'm good. I'm ready to go.
Right.
Let's do it.
Beautiful. Chris, that's a very good point. Yeah, this is, again, this is going to be a kind of an introductory part. I'm going to make this a little bit smaller there. And we'll be going deep into it in May. So just on that theme of being the introductory, if you've ever used the Gocator, gotten to the GUI, or used the emulator, and you tried opening up the surface filter tool for the first time, you will probably see there are a lot of filters. And that's why we put this together, is because if it's your first time using it, if you're not familiar with it, it might be a little daunting. So today we are going to focus on, if you look at the table, we'll be focusing on the left-hand side under the kernel filters. We'll be focusing on the erode, the dilate, the open, close, and median surface filters. And also towards the bottom, Chris is going to also demonstrate the surface curvature and the surface vibration correction tool as well. If you're familiar with this and you're looking at this chart, you'll notice that some of the surface filter tools will actually live in more than one box. So this is really meant for an introduction. But again, we'll get into that a little deeper in May. All right, and Chris, I'll hand it off to you.
Very good. So the first thing I want to mention is that the filters in the Gocator user interface reside in a couple of different places. So the first one is under the Scan tab. Obviously, I'll show you this in a moment here, but this is kind of at the acquisition side, although it is applied after scan, so you're not doing anything permanent to your scan. But the idea behind the filters underneath the Scan tab is that they're applied globally. And today we're going to look at gap filling and median. We're not going to look at smoothing or decimation today, as they're less commonly used. But when you're using the filters under the Scan tab, please recognize that they're being applied to the entire scan. And we'll talk a bit about where that makes sense and perhaps where it doesn't. We also have actually much larger set of filters available within the measurement toolbox, if you will, and can be applied as a measurement tool. These are nice because they can be applied to individual regions. So you can apply a certain filter in one region, a different filter in other regions to help you get to the measurement results that you need. These can also be applied in series. So within a single surface filter tool, you can apply up to 7 different filters in series to the same region. Perhaps most important distinction between these two, or maybe one of the best benefits of the measurement tool filters, is that they can be anchored. So you can apply your area of interest windows to certain areas, and you can anchor that to perhaps an edge of the part or a couple edges of the part. So as they float around, these filters will float around with the part. So let's jump into the screen and get started. So the first one that we're going to look at today is within the Scan tab. So you can see that I'm using the Gocator emulator here, and the Scan main tab is selected. And down here to the right, I've got my filter tab open, and we're going to take a look at gap filling and median in this example here. So you can see that we've got a simple small cardboard box here, and we've got some Lego blocks inside. really our raw scan looks pretty good at this point. And what we're trying to replicate here, if you will, is perhaps a packaging logistics type of application where a user may be interested in measuring the volume of the contents inside a box or other kind of carton. So this is an application that we see frequently, and the Gocator tool set lends itself really well to this. Now, despite the fact that the scan looks pretty darn good right out of the box, we do see that there's some dropout of data down in this area here on the blocks, particularly when we're applying a tool that's a volume tool like this one here. We really want to close off all of that as best we can so that we have a more accurate volume measurement. Now, since we really need to apply this to the entire scan set, the scan tab level filters really make quite a bit of sense. So I'm applying a gap filter tool here, 3 millimeters in each direction, meaning it'll close off a 3 millimeter hole. And you can see that it's really sort of closed off all of those voids that we saw before. And we have this really nice, consistent scan set inside, which will put us in a position to then apply perhaps a volume calculation inside this carton, right? And we've got that here, and you can see the search window. So just kind of jumping back to the scan tab, one of the things we notice is that we've also got some noise in here. And some of this has been introduced by the gap filling that I've applied. It's kind of connecting some dots here. That's not real data. And that's one thing you always want to keep in mind as you're applying filters, really to any device of this sort, is that you're manipulating the data. So you want to proceed with caution and not overdo it. So we really want to get rid of this noise because, again, it's potentially contributing to error in our volume calculation. And again, this is where the scan level filters really work nicely because we want to apply this median filter to our entire scan. I did a 1 millimeter stretch in each direction, and you can see there that it's really done a nice job of getting rid of some of that noise that we have in there. Again, moving on to our volume calculation, it's actually changed that number. It's made the volume greater because we've closed off those holes and we're using a complete data set. So those are a couple of the scan tab level filters. And again, the distinction is that they are applied globally always, but of course they're non-destructive. So if they don't work out for you, you can undo it fairly easily. So the next one we're going to take a look at is surface curvature. And in this example here, basically we're going to look at ways that we can take a curved surface and sort of flatten it out in our software so that we can apply different analysis tools to it. So in this example that I hope pops up here in a moment, we've got a smart speaker. So it's a cylindrical shaped object. It's got holes in it and it's plastic molded. So perhaps we want to look for defects that are common with molded plastic items like flash and that sort of thing. So here's our raw scan. It's pretty clear at this point that we've got, again, a cylindrical shape. This is molded plastic. Obviously, it's got holes in it. And then underneath that, we see, which is like a fabric nylon type screen that goes around the speaker. So, a typical application where this might be used is really defect detection. Is there flash? Is there other maybe debris on my mold that's not acceptable to the customer? So the first thing that we want to take a look at here is actually applying our surface curvature filter. And what that's going to do is it's going to analyze that curved surface, and it's going to pull out the curve and sort of flatten that. So unroll it or unfold it, if you will, to bring us back to a flat surface. This is beneficial to us because now if we have defects on that surface, they're really going to stand out both visually and mathematically. So the next step of filtering I did here is actually the use of a threshold filter, where we just kind of take one level, if you will, waterlining the scan data. And I did this to remove that mesh screen that's below the plastic. This is really just a visualization improvement, so I can get a better look at what we've got here. It also enhances our color map because we can now see deviations from the true cylinder because we're all flattened out now much more clearly. So you can see that, we've got some pink and white areas here all the way down to these lighter blues over here. Also clear at this point is this defect that we've got here in the plastic. So we've got some sort of anomaly here that really stands out at this point. Now, could we see it if it was still on a cylinder? Sure, we could. But this really puts us in a position now to quantify it. And we would typically do that by using the Gocator's surface blob tool. I've set up some criteria here to look for anomalies of particular sizes. And you can see that it's identified that right there. And we can also take a look at that being pulled out of the image on its own. And of course, our surface blob tool would identify any number of these on the surface, gives us a location of that, a count of how many we have, and what the size is. So it's really about defect inspection. So the next one that we're going to look at is vibration. And while this is loading, I'll talk a little bit about, the types of vibration that we see, where it comes from and that sort of thing. So this particular example is actually a steel strip. So it's, it's a steel strip that might be coming off a coil and traveling down a conveyor. Sometimes what happens when you have applications like this is because you've got a non-rigid part, there can be some vibration that occurs, particularly on the edges of the part, not so much in the middle. And what I've done here is I've actually cropped out the middle section of the steel so that we can really see where that vibration is coming into play. And sometimes this is caused by machinery in the area, in this case, perhaps it's caused by rollers, or just the motion itself causing a bit of, for lack of a better term, some flopping that occurs on the outer extents of the strip. So with our color height map here, you can see that there's a bit of a sine wave going on, right? That's pretty evident just from looking at the color map visually. So our surface vibration correction tool is obviously really easy to set up. It really doesn't have any settings in it at all. It's automatic for the most part. But if we just take a look at that corrected surface, we can clearly see that the software is pulling that vibration out of the scan. Why is this important to us? Well, in an application like this, we might be looking at something like a surface flatness tool where we want to analyze the overall flatness of this strip. Obviously, if we have curvature in there that's introduced by vibration or waves, it's going to be pretty hard to calculate flatness. So this is really useful for applications like this, or applications where you might have a roller conveyor that's introducing vibration that produces sort of a sine wave pattern in your scan. So the next one we're going to look at has to do with some of these kernel filters that Aaron mentioned earlier. So, the kernel filters are really doing manipulation to the size of the pixels, if you will, on the fringes of the data. So on sort of the outer edges of the data. And there are ways that we can sort of take the smaller ones and shrink them down, or take the smaller ones and expand those. And we might use that function for different reasons in processing our data to get good measurements. So this is a scan of a circuit board. And again, you can see here that really just the raw scan quality is quite good. I've turned on the height intensity map along with that, which is a feature that's relatively new for us. So we can actually see the grayscale from the print on top of this chip embedded in our scan. There are many areas on this circuit board which really could be measured easily just from the raw image because the data is quite good. But as we focus on some of the more specific locations, like for example, this chip here has a bit of a boss on it, and you can see that we've got a bit of drop out there, some missing data. It could stand to be cleaned up a little bit, particularly if you want to apply something like a surface circular edge tool to define the size and the location of that boss. You can see here it's working, but you can also see that there's a fair amount of data in the tool that's missing. So, to make this measurement robust, we want to have as much measurement data as possible. So jumping back to here, one of the things we might try to do this is what we call a dilate filter. And what a dilate filter is going to do is it's going to expand that data to sort of fill in the gaps. So it dilates these pixels, it makes them bigger, and it makes them crowd a bit to kind of close off some of those gaps. And that's what you see here. You also see here that I've isolated this window from the initial scan, and this is a great example of how we can use the filters in these under the tools diagram to process this sort of thing just in discrete areas. So I'm ignoring the rest of this and really focusing on this area and applying this filter to this area only. Now, one of the downsides to applying this type of filter, a dilation, is we've actually changed the size of that boss a little bit because we're sort of expanding it and closing off those open areas that we had around the edge. So what we'll probably do more commonly is, instead of just using that dilate, we'll use what we call a close filter instead. And what a close filter is going to do is it's going to apply that dilation, but it's going to follow it with erosion as well. So we're going to sort of fill up these pixels to close off those gaps. But once we do that, we're going to sort of shrink it back down with erosion so that we get back to our initial size. You know, we want to make sure that our measurement is still accurate. And you can see that after we've applied that here, that our measurement is within a single micron of the raw image. But the benefit to this is that we now have a lot more data being picked up by the tool. So we're defining our measurement with more data, which will make it more repeatable and more robust. So lastly, I want to talk about another kernel filter. This time we're going to talk about sort of working in the opposite direction and how we might use an open filter instead. So again, when we talk about dilating pixels, we're sort of making them grow. When we talk about erosion, we're sort of shrinking them down. And you know, those are used for different use cases, but where the power lies is really in combining the two to get to where we need to be. Okay, so this example here is a bit of a relic for most of us, I hope. A VGA connector. This is a good example of using filters to improve your data because this is a really shiny part. It's really, really small. You know, right out of the gate, not particularly clean. You know, we've got some noise there. You know, when we see an application like this, typically what we're being asked to do is analyze the location of the pins. Are they bent so that they're sort of out of place? Are they not seated properly so they're too short, too tall, etc.? So let's talk about how we can enhance this image here to make measurements like that more effective. So let's look at a surface filter, and I'm actually going to start just by simplifying this a little bit. So one of the first things I see in this raw scan is that I've got some noise. I've got some sort of floating data in between my valid data that could cause me some issues in terms of robustly identifying the location of these pins. So I want to get rid of some of that. So one of the filters that I might use to do that is an erode filter, where we can sort of take some of these smaller fringe pixels and we shrink them down or get rid of them. And you can see clearly that when I go between the raw scan and the eroded scan, that it cleans up quite a bit of that noise. You know, we've really removed everything in between the pins, and that's really our area of interest here. You know, but one of the side effects, if you will, of using that filter is it's also removed a bit of data from these individual pins, and ultimately what I want to do is properly locate them. So, you know, we're working in kind of the opposite direction as we did in the previous example. What we might want to do is use a closed filter instead. I'm sorry, not a closed, but an open. And what the open filter is going to do for us is it's going to apply that erosion, but it's going to follow it by dilation. So what we're doing is we're using the erosion portion to remove most of that noise that we're seeing around the pins, but then we're dilating again to make the pins themselves bigger than they actually are, so they're easier for us to identify. Now, what we would ultimately like is for these pins to stand out even more. So one of the things that we might do is come back within our filter tool here, and we'll change that number of filters from a 1 to a 2. And then I'm going to apply yet another dilate filter and add an extra layer of dilation. So even though this open filter includes both erosion and dilation, if I add another dilate filter in series, that gives me the ability to actually change this kernel value to whatever I want, and I can further expand the pixels to make those pins stand out even more. And you can see here that that's really clarified the pins for us in terms of location. Now, ultimately, what we want to do is find those pins. And of course, this is a good example of where we might use our surface blob tool again. So you can see here that the surface blob tool has easily identified each of these pins. We're not picking up any sort of extra stuff, if you will. That's the result of noise coming into play in between the pins. So in this particular example, we're really worried about location, not so much the size and the shape of the pin. So this works real well. All right, so those are some of the simpler kernel filters, if you will. Just jumping back into the slides. We'll do a quick summary, if you will. So gap fill and median, again, these often work really good just on the scan tab side because it's really helpful to just apply this to your entire scan set. Don't need to set up a tool, just let this go on your whole scan. Surface curvature tool, really helpful for identifying anomalies, if you will, or defects on a curved surface. And, it doesn't have to start out as a cylindrical surface. This can be spherical as well. Vibration correction, I think it largely speaks for itself. We're really removing that vibration from the scan so that we can focus on the actual part itself. The closed filter tool, a combination of both dilation and erosion that allows us to fill gaps but maintain size. And finally, in this last example, we've used multiple filters in series, open and dilate, to get ourselves from sort of a messy raw scan to a quite clean scan afterwards that allows us to locate the pins properly. And just, reviewing a bit, these are sort of the noise reduction and edge surface filters, if you will. The edge one is really the median filter particularly. Anytime we're eroding, we're discarding pixels near the boundary or shrinking things down. Dilation, of course, is the opposite. Again, these are, so we're applying this to kind of the fringes of different features there. So it's, boundary type process. And then open and close are basically combinations of those two, but in the opposite order. So that allows us to, fill gaps or get rid of noise, but then really get back to the original size of what we're doing. And then finally, median is an averaging of a chosen number of pixels around a particular kernel, and it's really used for noise reduction in the vertical or in the Z direction specifically. And with that, I will turn it over to Mr. Bobby Breyer, and he's going to talk a bit about the profile filter tools.
Okay, great. Thanks, Chris. So this is just a little add-on to the surface filter section. Profile tools are powerful if you're doing things in profile mode, or in the case of this presentation, when you're using a section of a surface where, let's say you had a curved edge and you want to know about the radius of the edge. We don't really have a tool that does that in surface mode. So you'd have to do it with a profile. So we'll be reviewing the scan tab profiles and a profile filter tool that was released in 6.1. One thing to remember with this presentation, we're only considering uniform profiles. We don't have filters for non-uniform or profile point clouds. In order to filter those, you would probably have to implement a nearest neighbor algorithm. From the results I've seen of that, they're fairly slow. So let's get started. So here's our original profile at the top, and I just took some screenshots of what different profile filters do to the original. Averaging and median filters are just the average and median point to point within a given kernel. And then we have our Gaussian filter. Most of the time you're going to be using median filtering just to remove some noise. It has the benefit of reducing major outliers, but it doesn't over smooth the data like an averaging or Gaussian filter will. We also have an interpolation filter. In the scan tab, this is closer to the gap filling, but it's done less intelligently. If you notice, we just essentially draw a line between the last point where we hit null data to the first point where we had real data. Okay, so let me show you some examples. This will be fairly quick. So here's a profile, and we have some gaps that, because of occlusion likely, we have a bit of a space here, so we might want to fill that. So I'm going to enable gap filling, and like Chris mentioned, this is a global effect, but it's a little bit more than that. Not only is it global, you no longer have access to the original profile, and if that's not important, then great, but if it is important, you should keep that in mind. And we have our median here, and if you notice, we have a Y direction. Well, we only have the X and Z axis that we're looking at, and in this case, if I were to enable Y, we would start considering follow-on profiles, or sorry, if this profile was, let's say, I, then the next profile, I-1, or the future one, I-1, we would consider that profile when filtering this one, depending on the kernel. Perhaps it goes out as far as like. And then we can also smooth it. Now, it does say smoothing, but really it's an averaging filter. It's the exact same thing. And then finally, decimation. If you ever have for some reason, if you have too much data, I don't know when this would ever be a thing, but if you ever had too much data, you can decimate it down and reduce your processing burden if you're just getting too much data. So there's a lot of, if you have like a 12 sensor setup and they're all profiles, maybe you do need to decimate just a little bit to stay ahead of the curve. Okay, so those are the scan tabs. Let's look at the biggest difference, which is interpolation and gap filling. So this is interpolation, right? We're drawing lines, and this is gap filling. So it's done a little more intelligently, and in my mind, it's a slightly more useful. Let's look at median. So if we zoom in, it's a little noisy. We can do a median filter. We'll increase the kernel size and take a look at it. Then we smooth it out. You can look at a Gaussian filter and the averaging filter. Those are a little more smooth. I generally stick to the median filter if I can help it. One thing to note is every time you filter, you lose information. So we try to optimize the video acquisition or the profile acquisition before we start applying a lot of filters, just because you are losing information. Okay, so let's go on to the next one. Here I have a surface, and I've taken section cuts of each. So here we're crossing it here. Over here, this one's vertical. We're going over a bunch of steps. And we're going to take a look at how to filter them. So maybe you're just trying to smooth these out. Well, just a simple median filter will do it, averaging filter. They're very easy to apply, and their output is another stream. So now you can use all of our profile tools on it. If we change our input stream to the vertical one, looks much the same, and maybe we'll want to connect these two here. So let's do interpolation, and there we have it. Maybe you want to smooth this guy out before you take a step size. Maybe you want to do averaging, and we'll just increase the kernel, and there you go. One thing to keep in mind is whenever I do heavy filtering, I do it to remove noise and to find generally the feature of interest I want, and then I can use the anchors I've developed from the over-filtered surface or profile and move them back to the original surface. So that's done very commonly as well. Okay, so that's pretty much it. Let me turn off screen sharing. And I believe that's all we had on the slide.
Yeah, that's great. Actually, so just speaking of some of those filters you were applying there, Bobby, I have a question come up from David asking, how does the gap fill tool and the dilation tool differ?
Mm-hmm. Yeah, I'll take that one. So the gap fill tool, I think some more thought has gone into how surfaces are stitched together. I want to say there's logic on the different layers and how they're expanded. It's definitely different from the dilation tool, but I can't tell you what the difference was when they're integrated.
Yeah, I think if I could just add to that a bit, I think my impression is that the gap filling tool is really more of a sort of connecting the dots, if you will, whereas the dilation filter is really more of a growing the dots to close that gap, if I'm not mistaken.
Yeah, that's great. David, I hope that answers your question. If not, feel free to reach out to us, training@LMI3D.com. Happy to go deeper into that if you like. So now's the chance. If you have any questions, if you're watching from home or the office, please put them in the chat. We've got 2 experts live right in front of you if you want to ask us anything. Maybe while we wait for questions to roll in, Chris, Bobby, anything for closing remarks?
Just want to remind everybody again that the follow-up will be in May, and we'll get into some of the more advanced surface tools at that time.
I just want to reiterate that over-filtering is okay if you're just using it for anchoring. Always try to minimize the total amount of filtering to just the bare bones of what's necessary and no more.
Mm. And I assume that's for 2 reasons. One would be the speed of the processing. It introduces a heavy load, plus you don't want to manipulate your image too much.
Yeah, that's right. The processing load significantly goes up as you start filtering more and more. And of course, every time you filter, you're losing information. So you really have to start wondering, how much am I drifting from the real thing? Perhaps your linearity will begin to take a hit if you start over filtering a lot.
Right. And I know that's advice from a lot of our field application engineers is, instead of over filtering, just focus on getting a good image in the first place. Cool. Looks like we have another question come in. For the surface curvature tool, does it have to be in a certain orientation?
I don't believe it does. Bobby? No, I mean, we've applied this sort of filter to spherical surfaces, right? So that, with curvature in every direction. So I think the answer is no.
Excellent. I see no contest from Bobby, so
it's
good.
On the same page.
Yeah, no, he's got it.
Cool. Good question from Alexander. Excellent. Okay. So I don't see any more questions coming in. We'll wrap this up for today. If you do have any further questions, once, say, for example, if you're watching the recording, you can always pop, if you put something in the chat during the recording, we will get that as an email. So if you have any questions that pop up later, you can put them in there or just send it to us at training@LMI3D.com. Chris, Bobby, thank you so much for going over this with us. And thank you, everyone watching from home in the office.
Thanks, everyone.
Thanks. Bye.
Okay. Bye.